I'm going to record this also on Zoom. But
recording in progress.
All right, well, we'll go ahead and get this kicked off. Thank you, everybody, for joining on a Saturday. My name is Heather Haas. I am the current president of the Dallas-Fort Worth Alumni Association at Michigan. I want to really thank you guys for taking time out of your day to learn more about the total solar eclipse that's coming up this Monday. So we hope we can offer some really exciting information and we can all learn. For those of us who might be in Dallas or Austin or various other cities that are in the line of the path. Before I get into that, though, I just want to mention one big thing that we do as an alumni club is be able to provide our members with various opportunities to learn and gather as a community, like today. But another big initiative that we do is help other future Wolverines in the area go to Michigan. And we are, especially in Dallas-Fort Worth, hitting a record amount of students who are getting into Michigan and wanting to go from the DFW area. So a big way we help support those students is through a local scholarship fund that recognizes these outstanding undergraduate students from the DFW area. So each year we've been able to increase the prize and the donations every year, and we can't do that without your help. And so I'm going to include a link in the chat. If you are willing to donate, that's our spot. But again, we want to thank everybody for joining. And I'm going to now move into the reason why we are here, which is the total solar eclipse. And so today we are excited to partner with the research group CoronaCast at the University of Michigan, the Department of Climate and Space Science and Engineering. CoronaCast is a graduate student-led partnership between the University of Michigan's Climate and Space Science and Engineering Department and the University of Texas at Arlington's Physics Department. And they are posted, we will see them very soon, they are posted up at UTA in Arlington, and they are here forecasting what we will observe during the total solar eclipse on Monday. They use advanced physics models. I'm going to let them get into a lot of those details. And on the day of the eclipse on Monday, they are going to have a live cast the entire day. So I am going to also include in the chat a great website with all of their information, all of their initiatives that they've been able to do, as well as that live cast that you can log in on Monday. But without further ado, I am going to pass it off to the team at CoronaCast.
Hi everyone, thanks so much for letting us talk to you guys about some of the cool physics that we're doing and some of the cool science behind eclipses. I think we're going to go around the room real quick and introduce ourselves. My name is Catherine Wilbanks. I'm a first year PhD student in the Climate and Space Physics Department.
I'm Dan Welling. I'm an assistant professor in climate and space, a University of Michigan alum, go blue, and formerly a professor here at the University of Texas at Arlington. And one of the things that is happening today is that for us, this is a little bit of a tech demo for our stream. So if you can't hear anything, if you guys can't see anything, if anything's wrong, let us know if it's too quiet or whatever, and we're going to adjust that on the fly. So I'm going to switch cameras here, and this is the rest of the team in the room. So what's been happening this week is we've all been in here doing science kind of in real time leading up to the eclipse. And I'm going to let this side of the table introduce themselves, starting with Chip.
I'm Jim Manchester. I'm a research professor at University of Michigan. I work on solar physics.
Shannon Liu, a first-year graduate student in climate and space doing the solar physics.
My name is Weihao Liu. I'm the second-year PhD student in the Climate and Space Science and Engineering Department.
I'm Amy Rewall, and I'm a second-year graduate student at U of M Climate and Space Department. I do magnetosphere physics.
And I should point out that as Heather said, we have a lot of students from the DFW area coming to the University of Michigan, and that includes both Catherine and Amy. So I'm really happy to have you guys in the department.
Bit of a temperature change.
Just a little. That's okay though. So do we want to jump in with a presentation?
Yeah.
So okay.
So we have a quick presentation for you guys where we're going to walk through kind of like what the science behind eclipses, what we can expect to see barring cloud coverage, And then we'll also kind of talk a little bit about our forecast for the eclipse, as well as some of the physics models that go into making those. So what is a total solar eclipse? It is when the moon passes between the sun and the earth, and it perfectly and is able to cast a shadow across a portion of the earth called the path of totality. So you can see here, it'll cast two kinds of shadows, an umbra and the penumbra, which is the larger kind of fainter shadow. That in the penumbra is where you get partial total solar eclipses, and in the umbra, that's the path of totality. That's a really cool spot that you want to be. The difference between 99% totality and full totality is like making a playoff game and winning the national championship.
Versus driving by the stadium.
Yeah.
Yeah.
So this happens not all the time. It actually takes a very unique set of circumstances because, well, first off, we've got the different phases of our moon, right? During a full moon, the moon is behind the earth, and that's when you've got the sunlight casting, fully blasting the moon's surface, and that light's all reflecting back towards us. Then in a new moon, that's when the sunlight's behind the moon and all that light is just reflecting back. So first off, we want to be in a new moon phase for a solar eclipse. But more specifically, the moon's orbit is actually tilted slightly to a 5-degree angle, and we need that angle to line up on the same plane. So you can see in the top left and the bottom right images, that's when that 5-degree inclination is actually level, so that we've got the moon on the same line. And it's then and only then that we can see total solar eclipses. So that's why they're so rare. So here's a couple of maps showing total solar eclipse paths just from 1901 to 2050. And you can see they don't cross through the United States that frequently. In fact, while total solar eclipses occur every 18 months, a specific location won't actually see one except for about every 300 years. That's why the last one that actually came across Texas was in 1878. And the US has only seen 15 in the last 150 years. So a little bit about what we're going to actually see. Barring cloud coverage, we're really hoping those clouds will shift on out of here. But at the very start of an eclipse, the moon will start to gradually start to cover some of the sun's disk, or the side of the sun that's facing us, and that's when you get the crescent shadows that you saw last year during the eclipse in October. You can see these in shadows of leaves. If you bring out a colander outside, that'll also make the same effect, and you can also do it if you spread out your fingers on both hands and cover them like that. That shadow will also show the crescent shapes. Following that, as the moon covers more of the sun's disk, it'll start getting darker around you. It'll kind of almost look like the sun setting. And at this point, it actually tricks a lot of the wildlife in the area into thinking that it's about to be nighttime. So they'll start coming out. You'll hear birds chirping. If we were a couple of months into summer, you'd hear the cicadas coming out. If you're further down in like central Texas, you'll start seeing bats coming out. And then as we get to 3 minutes before, this is when you can actually see the umbra, the shadow of the moon coming towards you across the landscape. So this is when you want to look out towards the west, and you'll see that darker patch coming towards you across the ground. Then we get to the really cool stuff and some of my favorite phenomena. So at about 2 minutes before totality, you'll see this effect called shadow bands. And this is when we're getting such a thin sliver of light coming through past the moon that it's actually getting interrupted by our atmosphere, by the air around us, and it's causing the lines of light to actually wobble around. You'll only be able to see this if you're looking at a large white surface. So you look at the side of a large white building, or if you bring out a sheet to put out in front of you, you'll be able to see the light dancing around on the ground. Then just seconds before, we get this really cool effect called Bailey's beads. And this is actually these are the bright spots that you can see on the outskirts. And this is caused by divots in the moon's surface. So right there where that shining spot is on the right of that image, there's actually a crater in the moon, and that divot is causing more light to come shining through. And scientists actually use this to map the surface of the moon to look for craters and valleys. Then that's when we get to totality, where the really cool stuff begins. This is when you can see the solar corona, or the outer atmosphere of the sun, with your bare eyes. So you can actually see right there in that last image, those pink spots outside of the moon's disk. Those are called solar prominences, and that's due to the sun's magnetic field, something that we're going to get into a little bit later. So throughout this time, just to kind of recap, all through that partial eclipse at the very start, that's when you need to keep your glasses on. Even if it's cloudy outside, even if you're only going to look up for a second, you always want to keep your eclipse glasses on. But once we get to totality, you're free to take them off. And for DFW, it's going to be about 2 to 4 minutes, depending where you are in the Metroplex, of totality. But you can download phone apps to figure out the specific time in your location. Then after totality, we're going to see all those same effects, but in reverse. And just like before, you got to keep your eclipse glasses on.
Go ahead, wait.
Okay. So 5 students of us form a team at the University of Michigan to predict the total solar eclipse, and we also have the management team that as you can see from the picture above, we have Connor, Shanyu, Catherine, Amy, and I. We also have Chip, Dan, and Judith here. And since the sun is the source of the Earth system, we also want to predict how the upper atmosphere, how the total solar eclipse make an influence to the upper atmosphere in the solar system. In the Earth system. So we also have the team at the UTA. That's the Minjing and Yu, and also Professor Yue Ding at the University of Texas at Arlington. So yeah, and actually total solar eclipse provides a good opportunity for us to observe the sun and also for model validation. So we are going to model the solar corona during the total solar eclipse 2024, and here's our timeline, and we are going to predict 7 days ahead and 3 days ahead and 1 day ahead of the solar total eclipse. But before that, actually, we have the 2017 and 2019 eclipse. So we were doing that for validating a model, and after that, we do the 7 days, 3 days, 1 day forecast. And next, we'll post our results on this website, and also due to the sparsity of the total solar eclipse, as you can seen before, we'll also do a live stream next Monday from the morning to the afternoon.
Excellent, yeah. And Wei Hao mentioned Yue Deng here at the University of Texas at Arlington, who has been a team member and a host for us. Yue is actually a University of Michigan graduate as well, so the Michigan connection runs deep. But now we're going to hand it over to Chip to tell you about some of the physics of what's going on in the sun.
Yeah, so that's an image of the sun, as we normally think of it. Just a ball of gas, bright and shining, and with a few irregular spots that we call sunspots, which happen to be dark simply because they're cooler than the surrounding atmosphere as a result of intense magnetic fields. With this, this belies an enormous amount of complexity and dynamics that are occurring in the outer atmosphere of the sun that can be seen primarily in the extreme ultraviolet above the Earth's atmosphere. And so if we go to the next slide, we get an image of just how extraordinarily complex and structured and beautiful the outer atmosphere of the sun is. This is seen in 4 different combined bands that are shown on the left. And this is in angstroms, so wavelengths of light that are being seen here, so much shorter. A tenth of it, the frequency, basically, a tenth of the wavelength of the standard visible wavelengths or less. And this frequency, we have a tremendous amount of emission because the corona is approximately 1 million to 2 million degrees, and at this temperature, the gas is highly ionized and emits very strongly in the extreme ultraviolet. And so what you see is where the magnetic field is seen as dark spots in the lower part of the sun, the photosphere, it's actually bright spots. It becomes very bright and emits very strongly in the extreme ultraviolet. So these bright loops, you can see a couple of concentrations of bright loops in the sun. These are really associated with active regions, and sunspots are actually below that. On the upper left, you see an erupting prominence. So this is actually occurring in the helium-304 emission. It's cooler material, there it is, and it's actually expanding outward from the sun. So these big loops will form, and occasionally they will erupt outward at very high speed. So next we're going to show some images of just what these erupting prominences look like. Again, this is cooler plasma at helium-304, and this is an erupting filament seen off the limb. So below we see all the structure of the chromosphere and how beautiful that is. Very granular, very highly structured, and then we see this enormous erupting loop, and it doesn't stop there. These just get bigger and bigger. We're going to go to the next slide, which shows an even larger eruption of a filament, and this goes almost halfway across the surface of the sun. You see it rising up gradually and then taking off. So these structures occasionally erupt from the sun and propagate into interplanetary space. And all of this is being driven by magnetic fields. And here now we see an eruption starting from the far right. The sun now is appearing basically as a little dot in the center of the green image, which again is in the extreme ultraviolet. And outside of here we have these other images are of Thomson scattered white light, which shows the density of free electrons that are scattering that light. So where it's bright is basically just where it's dense. And this eruption propagates from the sun. You see it there starting in the blue and then going into the red square and then finally into the larger blue circle. And on the far left is the Earth. And so we have these heliographic imagers in orbit at 1 AU, location of Earth basically in front of and behind the Earth, and they can provide these images of these coronal mass ejections propagating through interplanetary space. And the magnitude of these eruptions is really hard to comprehend. I mean, we think of extreme weather on the Earth. Winds are blowing around 150, 250 miles per hour in a hurricane or in a tornado, extreme tornado. In this case, by comparison, the sound speed in our atmosphere is around 700 miles per hour. So it's very subsonic. At most, you're getting up to maybe a third of the speed of sound. In this case, it's just the opposite. These eruptions are going at 3 to 4 times the local sound speed, driving huge shock waves and completely rearrange the structure of the solar wind. So very, very intense by comparison to our terrestrial weather systems. And we can simulate these. So this is a University of Michigan simulation of the sun. We're showing the sun right now. We're moving away from it. These lines are magnetic fields. This purple surface is the current sheet. And now an eruption is about to occur. We're going to show the shock wave blasting off from the sun and going through interplanetary space. And the first thing you notice is the enormous size. So not only is it very intense, it's also extremely large. And so the energy associated with this is of the order of 10 to the 33 ergs, 100 million 100 megaton bombs by comparison, enough to really strongly rearrange the system. And now you're seeing an impact on Earth. And so you're seeing this magnetic field structure and the shock wave impacting the Earth's magnetosphere and driving this very strong dynamics. And so now you see the magnetic field of the Earth extending from the poles and it being driven by the system. You see the magnetic field lines oscillating, and you see the auroral oval associated with the northern lights because you have energetic particles precipitating down the polar field lines and energizing that plasma. And now we get this extraordinary view of the coronal mass ejection still propagating from the sun, and this twisted spiraling magnetic fields propagating into interplanetary space, just absolutely enormous in scale. And these type of things happen all the time. We're at solar maximum, so we might have as many right now as 3 coronal mass ejections a day. So this is just how dynamic our space system is. And again, to illustrate the scale of the system, now we're zooming in on Saturn, showing its moons, of course, its ring, and also its strong magnetic field emanating from the poles. And here right now we also show the oval, the auroral oval of Saturn, and now we're zooming out again to show the scale of the system. And Saturn has a very, very large magnetosphere due to its intense magnetic field. And now we begin to show the scale of the entire heliosphere, of showing the magnetic field again. This now looks like almost like a bowl of spaghetti propagating out into the solar wind and impacting Saturn, which is 10 times as far away from the sun as the Earth.
So the fundamental challenge with doing these kinds of simulations, the simulations Chip has just shown, is that the space environment from the sun to the Earth to the other planets is a multi-physics and multi-length scale system. Sometimes you need to be simulating individual electrons and ions. Sometimes you need to be simulating the whole atmosphere as a fluid. And it's a really big challenge, not only in physics, but also in computational physics and computer science. So the solution that we have developed at the University of Michigan is to take different numerical models that simulate different parts of the system and couple them together to create this big self-consistent picture across the heliosphere that is still as efficient as possible so we can run it realistically on supercomputers. And this system is called the SWMF, or the Space Weather Modeling Framework. It's a flexible framework that allows us to execute, synchronize, and couple all these different models together. Development is led by Dr. Gabor Toth at the University of Michigan, but it's a big open source project, so we have a lot of people not only at Michigan, but at other institutions contributing. NASA, Goddard Space Flight Center, here at UTA, many institutions across the United States contribute and use this code. It's open source, so if any of you are very computer inclined, you're welcome to download and install the code. And another really cool feature of it is this in use in operations, and I'll tell you what that means here in a minute. To try to explain what this means, in this field of space science, scientists typically pick one part of the system to work on, right? Like you might have a specialist who looks at the solar corona, you might have a specialist that looks at the very top of the atmosphere, and we tend to write computer models to deal what we're interested in. And this leads to a bunch of different codes that do a bunch of different parts of the system. The SWMF allows us to plug in these different codes into different sockets, and we call these components. And the idea is that the components are somewhat arbitrary in that you can plug in different models to create different combinations depending on what you want to do, and then the SWMF couples them and gets them to work together. This is just a list of some of the codes that are available. You'll see a big one is BATS R Us, which has been developed at the University of Michigan. But I wanted to show you, this is an example of a simulation at Earth where this is the Earth and we're looking down at the North Pole. And this is one of those shocks that Chip described, draping around and driving dynamics in electrons and protons and magnetic fields around the Earth. And the square part on the bottom is what we call an adaptive mesh. It's actually the computer automatically determining where to put more computer resources and where to use less computer resources depending on how dynamic things are. So the last thing I want to mention real quick here is talking about operations. So all of this actually has a big impact on human technology, like GPS, the power grid, airline flights, and it's something that different government and private institutions monitor to make sure that these systems aren't compromised. So this is a picture, this is at NOAA's Space Weather Prediction Center, where they are monitoring the sun and near-Earth outer space 24/7. And if you look on this back wall here, these are actually results from the Space Weather Modeling Framework running in real time, trying to help forecasters understand what's happening at Earth so that they can send out timely warnings to interested parties, including power grid operators, the military, and folks like that. And this is an example of some of the forecast information you might see if you go to the website. And I'll put that URL here on the bottom for you. But essentially, if you go to swipsy.noaa.gov and under products, look for anything that begins with geospace. They call it the geospace model. You can see some of our real-time results that help us monitor what's happening in space in real time. And this is all part of the SWMF, which we, for this project, are using to simulate the sun and the solar corona and forecast what exactly you'll see at the moment of totality during the eclipse.
So thanks for Dan for introducing our space weather modeling framework. And now, given the technical but hopefully simple introduction on how we made the prediction of the solar corona. So basically what we're doing is to make a solar corona model based on our code, and we generate the observables that we're gonna see during the eclipse. So we're doing the model, and we can't leave out without the data, because we don't know what the sun will appears to look like without the data. So the first thing that we're going to do is to collect the observations of the solar surface and magnetic field from the previous observations. But unfortunately, that we can only see one part of the sun, that is the space in front of us at one specific time. So we're gonna collect the data through the whole rotation period of the sun and collect the magnetic field at different places of the sun to make a whole map, as you can see in the second panel shown here. So this is basically the distribution of the magnetic field at solar surface throughout its whole rotation. And based on this data, we run the simulation based on our code that is awesome code. It has an awesome name, so it's called awesome code. And then run the magnetic hydrodynamics simulations and consider a series processes like the radiative cooling, heat conduction, and the output with heating happening in the solar corona, and give us a very realistic distributions of physical conditions in the solar corona. And based on these data, we generate the observables and visualizations from it. And shown here is our model of the 2017 eclipse solar corona model. And it's an ultraviolet image that generated from our model. And you can see how beautiful it is, showing different parts and structures in the solar corona. And in this slide, we're showing a preliminary experiment for our eclipse prediction this year. So we're trying to produce a 2019 eclipse event using our models and techniques. So here I'm showing our model outputs versus the real observation 5 years ago. And the first viewer is showing the visualization of the magnetic field from our model. And the panel C and D down below are showing the white light signals that our naked eye is going to see during the eclipse. And they are both from the model. And the panel B, that is in the right top, we're showing the actual observation of the solar eclipse during the 2019 event. And you can see how similar they are. And so we're applying the same process, modeling and treatment of the data to exactly the eclipse this year. And we'll keep updating the model and our predictions. So here I'm basically showing a prediction and the observables generated from our prediction model that we made about 2 weeks ago. And the left viewer showing the white light image, and the right one are showing the UV images. So we're still keep updating the model, and a few moments later, are going to show some very up-to-date results that is better and more beautiful.
So there's actually a few unique opportunities for you guys to get involved too. There's 2 citizen science projects that I'm going to outline. This one is called Globe Observer, and it's an app that you download on your phone, and it'll track the cloud coverage change during totality, as well as the temperature change during totality. And then they compare it across the entirety of the United States and see how these things differ during totality, because we see clouds will shift out of the way because the sun is being blocked by the moon, so we're no longer getting that heating of our atmosphere. You'll actually feel the temperature dip about 10 degrees during totality. And then the other one is called Sun Sketcher. So those Bailey beads that I talked about earlier, this is a citizen science project for scientists to track these happening across the path of totality. So this app that you download just takes photos of the eclipse throughout the process, and then they find the photos that involve Bailey's beads, so that way scientists can look at different structures in the moon's surface. And again, here are the QR codes for both our website and for the live stream that will be happening on Monday.
So at this point, we're going to switch to the view so you guys can see all of us here. And, oops, and Heather too. I'm going to switch off of Heather. I'm so sorry, Heather. And we're going to replace Heather with the most recent forecast that the team has made. And Shanyu, if you want to talk through what they're seeing with these different pictures.
Oh, sure. So we're now making 4 models with 4 different sources of the solar magnetic field prediction. So we're running 4 magnetic hydrodynamic simulations and generate 4 different sets of observables and visualizations for each of them. And each panel is now showing the one specific model. And here we're showing one. Oh, okay. So let me talk about this first. So
it rotates fast. I'm so
yeah,
sorry. Yeah,
it's fine. So Here are showing 4 models with 4 generated observables, and these are the white light that we're going to see at the Dallas, Texas. And here are the UV observables that are ultraviolet images combined with different wavelengths of the 4 models. And here comes the structure vector, that is the rendering of the magnetic field in the solar corona. And here's a structure vector outside. You can see the magnetic field stretching out in different models. And here's a rotation of the magnetic field. You can see the structure at different viewpoints, and it's rotating. And here comes back to the white light. And so it's noticed up with the Dallas and Texas viewing point. And we can see so many similarities through the 4 images, but still we can see some differences among them. So our 4 sources of the magnetic field maps are very similar but a little bit different, which tells us a lot of information of our data and the model.
Yeah, it's a couple of the unique things that happens with this team compared to other teams trying to do these forecasts is not only the computer model that we're using, but also the amount of data that we're bringing in. We have predictions from 4 different data sources to help give us a range of predictions. During the live stream on Monday, not only are we going to talk through these predictions in a little more detail, but as the first pictures come in from the eclipse itself, we're going to be doing real-time data model comparisons, and you'll see what it's like for us to do like science in real time, which may be a combination of excitement and also disappointment depending on how things go. And we're hoping we learn something about how the different forecast techniques that are being implemented give us different ranges of good and bad comparisons to the data. So the pictures that are cycling at the bottom of the screen right now, those are on the website. And when we have our last set of forecasts, our 1 day ahead forecast that we would hope would be the most accurate, we'll put those on the website so you can see them as well. Overall, this has been a tremendous effort from Chip, Xiaoyu, Wei Hao, Amy, and Catherine. It's the amount of work they put in this week and everything leading up to this just to get the pictures on. Catherine, how many hundreds of students have you talked to this week?
I think close to 400 students in the Arlington area.
Yeah, and then having this opportunity to talk to you all today is a big deal for us. We really appreciate it. So at this point, we're really happy to take questions from Heather, and if you have any, or anybody in the audience.
Yeah, I was going to say, if anybody wants to, definitely feel free to unmute yourself and ask any questions that you guys might have. But really awesome information. I guess one question I have is, you mentioned that the weather will change when the total eclipse happens and things like that. And obviously now the weather forecast is showing some clouds and some potential storms. So when you mention that the weather will change, how drastically do we expect that to change, if at all?
It won't be very drastic. It'll be subtle changes. Like, you're not going to be wanting to go grab your winter coats out of the closet again all of a sudden. It will be very minute changes, but something that you can definitely observe. So the wind might calm down a little bit. It'll get colder. We're hoping that the clouds will actually clear out a little bit, especially if we have high latitude clouds and not low latitude clouds. That's kind of, I'm sure you guys have been hearing that on the weather. We're looking for high latitude, not low latitude ones. But yeah, we can see some of that happening because what's essentially happening with the moon passing over perfectly across the sun's disk is we're shutting off our heating source for the Earth, for our specific location.
In that one spot.
In this one spot. If we were shutting it off for the entire planet, it would be very bad.
Yeah.
But with that comes those subtle changes in the atmosphere.
Yeah. I was there, and so was Chip, for the 2017 eclipse, and you definitely feel it. It's this weird feeling of it becoming dusk really rapidly, and you feel that cooling. I don't know, Chip, do you have any reflections back from when you were there in 2017?
Oh, just the experience is absolutely incredible. I mean, to see this intense area of sunshine, that you're so used to that you can never look at because it's so bright, it would burn your eyes. And then suddenly it's completely black. It's just gone, right? This body of eternal light that we rely on is suddenly nothing but a black circle. And you can now suddenly see this part of the corona that we look at all the time with instruments, but we've never before seen with the naked eye. And it actually really exists. Our instruments didn't deceive us. Our models aren't deceiving us. This thing really exists, and it's bright, it's beautiful, it's structured, it's the color in it from the base is amazing, the deep red that comes from the H alpha line and the chromosphere, and this transition it makes, it's absolutely extraordinary.
Yeah. So, more questions.
I have a question.
Go ahead. You go.
So, thank you, Dorothy. I have a question about how fast is the shadow going to travel? And I also read about a flight that they were marketing. One of the airlines was going to try to fly so you could watch the eclipse, but I wasn't sure like which direction you'd have to travel to see a good show. And I'm just curious what your thoughts are on the speed of the shadow, and if you were devising a flight plan, what would it be to see the most of the eclipse that you could?
You're definitely testing our knowledge limits already, so we love it. But so we have in the past, scientists in the past have traveled along the path of totality across the whole stretch, and it takes really fast planes because you got to think you're factoring in the speed of the Earth rotating and the speed of everything moving across. Yeah. So most of the flights that are being offered this go around, I believe they're only seeing a portion of the path of totality.
Yeah, I can't remember how much time they're going to actually see it. Yeah.
There was a particularly sharp student at one of the Arlington high schools we visited who was talking about one of the total solar eclipse. They tried to fly a Concorde jet to keep up with it.
And that was still struggling.
Yeah. Chip, do you want to talk about ACES real quick?
Yes, there's an NSF-funded mission to observe the eclipse from high altitude in an aircraft, actually right here in the Texas area. And so they're going at high enough altitude to measure the sun in the visible line. So what we were showing before, many of the images are in extreme ultraviolet, which cannot be seen from the Earth's surface because of the atmospheric absorption. And so what we see are the visible lines and infrared lines, but they're greatly enhanced if we can go higher up in the atmosphere to avoid the atmospheric absorption. And so this is just what the spacecraft or aircraft will do. It's going to go up to high altitude, 40 to 50,000 feet, and have an observing window in the side of the spacecraft, allow that sunlight to come in, go through the telescope, and they can actually observe these spectral lines that again are in the visible spectrum and the near infrared. So that gives us a lot of information we normally don't have. The moon is the perfect coronagraph. So there's nothing that compares to that in terms of blocking out the photosphere and allowing that part of the visible light to come from the corona, which is normally 1,000,000 times fainter than what's coming through the photosphere. So the only time you can really see that part of the light, the visible part coming from the corona, is only during a total eclipse. And so this is why it's really valuable to be able to make these measurements specifically in the visible spectrum and can be done from Earth when the moon is blocking out the photosphere.
So I hope that answers your question. We kind of...
Well, the first part of it as well, for us here locally in DFW, the whole process will go from about noon to 3 p.m.-ish. So we'll start seeing the moon starting to occlude part of the sun around noon, and then totality will be around 1:40. That it's going to vary across the metroplex because we're so large, but roughly around that time. And then totality will end about 2 to 4 minutes, depending where you are, and then it'll be back to a normal sunny day by 3. Well, maybe not sunny. We may be looking at some severe weather, but it's Texas for you.
I'm curious if any of you have ever heard of a woman named Leticia Ferrer. She wrote a book called Texas Solar Eclipses. And of all the different backgrounds she has, and this is just a hobby for her, she's been obsessed with eclipses since she was a little girl, and she's literally attended every single eclipse in the world since 1998, including going through 7 continents and 6 different oceans, seas and oceans. And in fact, she was one of the few Americans that got a passport, a visa to Argentina in 2021 during the middle of COVID. to go down and see that one. And she went to one in Australia, which lasted all of 50 some seconds. She said, don't ask me what that cost me. I don't want to do the math on what it cost per second to be there. But she's done more. I first heard about her at a talk she gave, an after dinner speech at my Association of Women Executives here in Dallas. And she said she's going to go to Hillsboro to see the eclipse. She thought that was the best place in Texas to go, in Central Texas. I'm really worried about the weather down in Hillsboro for this event. So anyway, I didn't know if you've run across her, if any of her work could be of help to you or back and forth. She's not as scientific as you are, but she might have there might be some collaboration that would be useful. I don't know. Anybody heard of her?
Yeah, I haven't.
No.
I'm afraid not.
Well, she's
Yeah.
got a book on Texas solar eclipse. It's the name of her book, which is it's a layman's book, but still, it might be worth seeing for all the work you've been doing in Texas, especially,
For sure.
For sure, especially if she's going to be taking some great photos that we can maybe compare to.
Exactly.
But like you said, we're all worried about the weather.
Well, she's got great historical photos that we saw in her presentation. She did a Zoom call just last Saturday,
Oh,
and it
wow.
was for an hour. And I can forward you that if you want. It's about 50 minutes, and it's got all kinds of neat videos that we didn't get to see it at the talk she gave because her computer wasn't helpful. So we just got the verbal stuff mostly. But yeah, I mean she's just, I've never been in a totality. Closest I got was in 2017, where we had about 2/3 coverage in Texas, in Dallas, which I understand is nothing the same as the whole
actually,
thing.
most of us have not seen totality. Pretty much all 4 of us students have not seen totality, so we're really hoping that we get the chance.
So
You're going to be in Dallas for this one, or are you going somewhere else for the actual viewing?
We're gonna be in Arlington, so we're gonna be in this room most of the day, and then we'll be booking it outside to one of the parking garages to get up to the top to view it, and hopefully the clouds dissipate a little bit or enough.
Yeah.
So is Arlington the best part of the Metroplex from a viewing standpoint, or is it just because you're there and you got the
It's
structure?
mostly because we're mostly because we're
I
here and we
understand.
wanted to be. We're performing the live stream and
Oh,
all
sure.
the
You
work
gotta have all
Here.
from this room. You
Yeah.
can see our
Yeah,
scribbles.
all your
everywhere.
logistics. Yeah, I got it.
Yeah.
So you're kind of pinned to that location. Well, hopefully it'll be a great one for your sake and everybody's sake that you have that. So I know they used to say there was going to be fairly good in Texas, in Dallas. I mean, the South Texas, San Antonio and Austin were in real trouble, but by the time we get to the North Dallas, it was going to be better and better and better. I'm in Coppell, the far northwest part of Dallas County, and we thought we were going to be the best of the business, but that keeps getting worse and worse by the day, so now I don't know what to think.
Yeah.
I have all my friends out there praying for clear skies, clear skies, keep praying for clear skies.
Yeah.
But she
Hopefully
did have a great
so.
video of it being seen through a cloud coverage, which gave me hope that even with the like you said, those high clouds, you'd be able to see almost everything.
Yes, so even with high cloud coverage, we'll still be able to see some of the, you won't be able to see stuff like the Bailey's beads, for instance, but a lot of the other phenomena you'll still be able to experience to some extent.
Yeah, better than nothing.
Yeah.
Here's another question. I'm going to be observing from the Fort Worth Botanic Garden. And
Oh, yes.
for what's happening with plants, flowers, etc., that there was like an opening or closing. What might be some other observations to look for?
That's a tough question. One of the you mean observations from your point of view, just on the ground?
Yeah, as to what might be happening with plants. And also, Heather, I had just sent you an email that if you wanted any kind of a connection with either the garden or the Botanical Research Institute of Texas, I'd be happy to make a connection there.
Oh, yeah, for
Yeah.
sure. I mean, I've been going to the Botanic Garden since I was all of 2.
Wonderful.
Big fan. But, no, yeah,
That's
so.
a really good question about.
Yeah, because
plants.
there are a lot of
Yeah.
plants that open up during nighttime or during the
Yeah.
twilight. So I honestly don't know if they are going to think that with with it becoming dark around us, if they will also be tricked into it.
Yeah.
I would imagine so, because they wait for those triggers like the air temperature and the sunlight to, either open up or close up at nighttime. So
I will say that a lot of our understanding of the biological responses to the eclipse are still an unknown. So you and other people being in the botanical gardens, you are potentially a new data point. So anything that you see could be the first time someone sees it.
And there's also been ongoing the butterfly exhibit in the
Yes.
conservatory area. So just seeing what might happen with the butterfly aspect could be fascinating.
Oh yeah, for sure. I mean, like I was saying, insects fully think that we're going into twilight or we're going into, the evening, so they begin to react accordingly. It's a really interesting phenomenon.
One thing I want to share with you from Letitia, and I just rewatched her video this morning, or I would have forgotten this. She says the perception of color shifts. She's got a whole thing, and a scientific word I don't remember for that, and she's going to wear red pants.
Yeah,
and her,
that's right.
On his shirt, but the red pants, she says, red goes. Can you speak to that more specifically? More authoritatively?
Not more specifically. It is something I'm aware of, and you talking about it just now, I'm like, oh my gosh, I forgot about that whole effect, and
yes,
I'm wearing red pants right now. I picked the wrong day.
Yeah.
Well,
So
apparently it dramatically shifts how our eye perceives the color because of the totality. It becomes very different. Not just like it is in a dark room, in dark red at night. No, it's not the same thing. It's a whole entirely different scientific effect on how we see color in a totality, which has a scientific name to it. So that's all I can tell you, but it's in the video that I have.
Yeah, I could comment on that. So
Pardon me?
during normal daylight, what we see from the photosphere is essentially a black body spectrum. That's what you normally have as a thermal spectrum, which covers a wide range of energy over in this case, over the visible spectrum, which is going to be somewhere from 300 to 700 nanometers. And so when you go into a total eclipse, that suddenly changes. You lose that light that's coming from, that's in equilibrium. It's in a black body spectrum that's coming from the photosphere. You lose that, and what you have now is light coming from specific emission lines. The number one line in the chromosphere, at the base of the atmosphere, you're going to see is coming from H alpha, and that's going to be very intense red light. And then you go higher and higher in the atmosphere, you're getting lines. There's a green line in particular. There's a whole line. The lines coming from ionized oxygen and iron, and we could look at those, but they have very specific temperature or very specific frequencies in which they're emitting. And so that changes things. You suddenly go from basically a very, very broad spectrum of light being emitted to basically a picket fence coming from very specific frequencies from specific atoms. This H alpha is coming from hydrogen, and then you have emission lines coming from oxygen and iron lines. Perhaps, Sean, you might know some of the specific lines and their colors.
You mean the UV images or the
white light, or excuse me, the visible light images that we make.
Oh, the visible. So we're now also making some specific spectral lines within the visible and infrared wavelength range, and we're actually mainly focused on some iron lines and some silicon lines. So there are actually a great lot of different kinds of irons in the solar corona, and they're emitting some specific lines with specific wavelengths. So we're gonna observe them. We're gonna look at the spectrum and see how they reflect the physical conditions on the solar corona, and see what we're gonna learn about the streamers, different structures, and their temperatures and different physical variables from these spectral line observations.
So we could look over that and look at the brightest, the most intense lines in the visual spectrum. But basically the effect would be from having a normal light bulb, especially an incandescent light bulb, which is specifically also a black body thermal spectrum, to emission coming from like LED at very specific frequencies. So you simultaneously have a green light, a red light, maybe a purple light. And so you have these light surfaces, these light sources that are being mixed, but each one is at a very specific frequency.
I hope that answers the question a bit more.
We are, I full caveat that we are very much scientists.
and huge nerds.
And very much computer, model-driven scientists. We don't, looking into the biology of things happening and stuff like that. That has all been new ventures for us on this project.
Yeah.
They're definitely not our areas of expertise.
So in a nutshell, bring your white sheet to lay out. Bring your colander to
Yes.
see. Of course, you gotta have your glasses.
Of course.
Wear something red shirt, red pants, and be around something red. If you got red flowers, that's a great thing to test with.
Yes.
Be where you can see the leaves of the tree and the shadow they cast, but not too much a big tree to take up your sky space. Anything else we need to be thinking about as observers?
I think for DFW specifically, try to stay put. Bring snacks and stay put.
Yeah.
Yes.
And a lot of times people recommend there are apps
that you can get that will alert you to when the glasses off, glasses on timing is.
Yeah, because even just a few seconds of staring up at the sun, it can damage your retinas.
And I have a question on, we're talking about this total eclipse. Are they already, or are you guys already focused on the next one? Are they talking about where it is, in the future and kind of that realm?
Oh gosh.
I would say the predictions of the corona, getting these images, that is a lot of work. It's testing the limits of our model. It's testing the science that we've done over the past couple of years, and it was a lot of work getting to this point. And the images you're seeing on the screen, in the room yesterday, there was audible relief when these started coming through, and then excitement when we put them on the web. So this is a very long way around of saying, I think right now we're going to take a breath, and the next step is archiving everything we've done, from the scripts, the computer, the steps we took, the settings we used, and use that as a stepping point for the next one. And we'll start making plans, I think, once we've had a breath and have archived things from there.
That's awesome. Thank you for that. All right, are there any questions? I think we are coming to the end of the session, so I wanted to see if there were any other questions out there for the audience.
Did you say you had a link we could use to figure out exactly the totality in our area, much less the cloud cover to be expected? Anything? I think you said something about that, but I wasn't sure.
Yeah, there's an iPhone and Android app you can get on your phone. The names are, give me 2 seconds and I'll be able to tell you. If you just search Eclipse in either of the app stores for Android or Apple, the one that I've used before is Solar Eclipse Timer, but there's a number of others that do very similar things.
Thank you.
Yeah.
It'll help keep the times specific for your location, because I know I gave very broad timing.
Well, I know we're very lucky in Dallas. We're just under 4 minutes, which is quite an,
Yes.
I understood from Letitia, having seen 20 plus eclipses, she says a minute to 2 is typical.
Yes, this is one of the longest lasting eclipses that we've seen in a while.
What were you going to say,
And for us
Chip?
to be,
Oh, that's exactly right. I mean, 3 minutes is a pretty long lasting total solar eclipse experience.
and we're just under 4 minutes here. And
Yeah.
if the farther south you go, Letitia was going to, where it was going to be 4.24, 4 minutes and 24 seconds. I mean, that's unheard of practically
Yeah.
in the eclipse world. Assuming they get any sky to see it with.
Yeah, for sure.
Awesome. Well, if there aren't any more questions, I want to again thank you guys so much. Thank the entire CoronaCast team. You guys are doing amazing work. Again, we have shared those links. Make sure to log on to their live cast on Monday. Check out their website, ways to support them. We really, really appreciate all of your efforts and want to thank you for all of your information today.
Of course,
As a
thank you
Dallas
guys.
person with a Michigan degree, thank you for representing
Blue.
both places.
Yeah.
Great job. Bravo, bravo,
Yes.
bravo.
Awesome. Thank you guys. Enjoy your day, and let's all hope for really good weather on Monday.
Yes.
Clear skies, clear skies.
Yes.
Clear skies.
Awesome.
Our
Well,
mantra.
thank you guys. Have a good day.
You
Thank
too.
Thank you for doing
You
this.
too.
Thank you for doing this.